Hello, and welcome to today's session on the independent samples ANOVA. As always, before we get started, please make sure to print out the PowerPoint lecture notes and have them in front of you so that you can make notes along the way. Today we'll be introducing the independent samples ANOVA conceptually. We'll talk about some numbers, but most of this will be just about ideas. We'll get into some heavier computation a little bit further on in the semester. After we introduce the concept of the ANOVA, we'll also remind ourselves about something that we learned earlier. This was called the equal variance assumption. It's one of the three assumptions that we typically see in parametric testing, and the ANOVA is indeed a parametric test. So we're going to revisit that and understand why the equal variance assumption is an especially important assumption in the ANOVA. Finally, we'll introduce the idea of the cumulative type 1 error, and also how we might begin to correct the cumulative type 1 error by something called a post hoc test. This is an entirely new idea that arises only when we come to the point in the semester when we're talking about ANOVAs. Okay, so for a little bit of context, let's always remind ourselves that as psychologists, we're interested in real-world phenomena, just like other scientists are interested in real-world phenomena. Our scope, in terms of the content of psychology, would be behaviors, thoughts, and feelings. So we're looking at some real-world behaviors, thoughts, and feelings. We'd like to investigate that scientifically. We begin by creating a research representation, and we do that through primarily two processes. First, we engage in some sampling. We might need to take a sample of people. We might need to take a sample of non-human animals. But in any case, we're going to be taking a sample, and we have talked about lots of different sampling techniques in this course. We've also talked about creating our research representation by abstracting by way of operational definitions, where we state the operations that we use for measuring whatever construct it is that we want to be measuring. Once we have something manageable, something that we can actually explore in a practical sense, we're going to engage in any of three methodologies. These include observation, experiment, and surveys. And once we have those conducted, we'll have some research results that we'll need to analyze. Today we'll be spending lots of time learning this new data analytic technique called the ANOVA. And just to put it into context, the ANOVA is an inferential statistic, as is true for the t-test, which we learned fairly recently. In fact, you'll see that the ANOVA and the t-test have quite a bit in common. Other tests that we've used for inferential statistics have included the chi-square, and we've had different varieties of chi-square statistics. We've also used the R statistic as well. All of these data analytic techniques hopefully give us some research conclusions that we can generalize back to the real world in our scope of behaviors, thoughts, and feelings. So let's begin by trying to introduce the independent samples ANOVA conceptually. And we'll start out with a potential pop quiz question, and this time I'm going to do something very unusual. I'm actually going to give you the answer to the pop quiz question. Usually I don't. Usually I encourage you to go to the readings or go to the web and pull out your own answer, because I'm very interested in teaching you how to fish rather than feeding you a fish. But right now I really want to make something extremely clear, so I'll depart from my typical procedure and I'll give you the answer to this one. First, let's just read the question. The question is, in your own words, explain why a researcher would choose to use an ANOVA rather than a t-test. As I've said, the ANOVA and the t-test are really quite similar in many ways. They're both parametric tests. Both are actually comparisons of means. Here's how they differ, though, and this would be the answer to the question. They differ in that the ANOVA can be used to compare more than two means at once. By contrast, the t-test can only compare a maximum of two means at once. So if we have a study where we're comparing many, many means to each other, the ANOVA is appropriate. Whereas if we're comparing only two to each other, we could use an ANOVA, but we could also use a t-test. And sometimes the t-test is computationally simpler. So we might use a t-test if we have two means, although we could use an ANOVA for two means. But the real benefit of the ANOVA is when we have many, many means. Okay, what we can say too about the ANOVA is, just like many of the other examples that we've seen this semester, the ANOVA is all about ratios, 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 one number over another number. I promised that would be a recurring theme even in the first week of class, and here we see it again for the ANOVA. So we'll consider some concepts that you've already mastered that you probably don't think of as ratios, but they actually are ratios. Earlier in the semester we introduced the z-score, and computationally the z-score was the observed value minus the mean, and that difference gets normalized by the standard deviation, shown here as sigma. So this all by itself is a ratio, and this gives us a standardized score that we call the z-score. As a reminder, z-scores were important because they allow us to compare across different kinds of dimensions. Essentially and figuratively, they allow us to compare apples to oranges. Here's another statistic that you might not think of as a ratio, but recall that the t-statistic is really about differencing two means, the mean from one group minus the mean from another, and putting that into some context or normalizing it by some pooled variability. As we said in an earlier presentation, this pooled variability is really quite a complicated computation, and we're not going to be doing that today, but what we do want you to know is that the t-statistic really is a ratio. We consider the difference here within the context of variability, just as we had done over here for the z-score, the difference between the observed score and the mean in the context of some variability. That's true for the z, that's true for the t, and you'll see that's also true for the ANOVA. Like the z-score and t-statistic, the ANOVA, analysis of variance, is also a ratio. Okay? Like the t-test, the ANOVA is used to evaluate the difference between means within the context of variability. In fact, this was even true in the chi-square. We had looked at the variability that we might expect, and we had expected values, and we asked the extent to which our observed values were differing from our expected values. The ANOVA is distinct from the t-test, however, in that the ANOVA can compare multiple means to each other, as we mentioned earlier. The t-test is stuck at a maximum of 2 comparisons. And of course, we also have the one-sample t-test. We can compare one sample of scores to some standardized mean that we might get from the literature, or we might have some governmentally dictated value that we have to compare to. Okay, let's compare the t-test and the ANOVA a little further. Here's the t, here's the ANOVA. The ANOVA will be signified throughout this presentation by an F. F is the first letter in its founder's name. That was Fisher, was the researcher who had developed the ANOVA. So in honor of Fisher, we frequently call the ANOVA the F statistic. And we'll be using those terms interchangeably. The ANOVA is the F statistic. So here's the t, here's the F or the ANOVA. First, let me start in the center and just remind you of what I think is a cool factoid, and that is that t squared equals f. They really are that relatable to each other. If we square an observed t value, we would get the f value that we would have obtained had we run an ANOVA rather than a t-test. Correspondingly, of course, we can take the square root of f, and that would give us plus or minus t. As you'll recall from your high school days, or maybe even junior high school days, when you take the square root of a number, you have to allow for the possibility that the answer is either plus or minus, positive or negative. So getting back to the t-statistic, as we saw a moment ago, there's the mean difference. That was x bar 1 minus x bar 2 over some kind of pooled variability. We might call that the standard error. Conceptually, we're looking for the difference between the samples versus the difference expected by chance. All of these are inferential statistics, and we're trying to figure out to what extent means might differ, and are they differing only by chance, or are they differing significantly? And so we have the same kind of idea going on here for the F statistic, which we said is our ANOVA. We're looking at variability between treatments versus the variability within treatments. And I'm going to pause for a moment here and ask you to jot something down on your PowerPoint lecture notes. Throughout this lecture, we're going to be referring to this particular ratio, this F ratio, as the variability between treatments or between groups versus the variability within treatments or within groups. And one of the ways to think about, and maybe to recall, which one is in the numerator and which one is in the denominator, is to remind yourself that B comes before W in the alphabet. So we can simply alphabetize these two words, B up top, W on the bottom, and you have the ratio. The variability between treatments, the variability within treatments, stated one other way, differences between samples versus the differences that we might expect by chance. And we'll see this lots of different ways today so that we really get a hang of it. Okay, so whenever we are measuring behaviors, thoughts, and feelings, in whatever real-world phenomena we might be investigating, we're going to have to come to grips with the fact that scores vary. It's a fact of life. And they vary for lots of different reasons, and we're going to zoom in on 3 of these and begin to understand how we can take those varying scores and maybe partition them in a way that would make sense in our analysis of variance. So let's go through these one at a time. One source of varying scores or variability would be the treatment effect. The different levels of the independent variable may cause variations in scores. Remember that the independent variable is the variable whose effect we seek to know. And usually we're hoping that a lot of the variability in our data set is driven by this. It might be the case that we are clinical psychologists and we're trying to drive down depression scores or drive up mood scores. We're hoping that our treatments might be effective and are actually the source of the variability. This is usually what we're interested in. That being said, there are at least two other sources of variability that are something that we have to account for, but are something that are independent of the treatment effect. The first of these would be individual differences. Participants enter an experiment with different abilities, motivation levels, experiences. People are unique. Individual non-human animals are unique. So we have individual differences that are driving our variations in scores, independent of whatever you and I might be doing with our treatment effect. Okay, our third source of variability is what we call experimental error, and this might be the source that's perhaps least clear to most students. It's a little bit more abstract. When we're thinking of experimental error, I hope you'll make a note in your PowerPoint lecture notes saying that experimental error is experimental variability. Okay? So let's remind ourselves that whenever we make a measurement, there is some amount of error, and error doesn't necessarily mean a mistake, it just means a margin of variability. Wonder if we can think of it this way. If you and I are drawing a graph for two groups, we'll have the mean of the first group come up to here, we'll have the mean of the second group come up to here, and we'll put some error bars on those. So basically, when we put the error bars on there, we're conveying to our audience that we believe that the scores might have a central tendency of a particular value, but they also have some dispersion. And we've talked about how in descriptive statistics, we indicate some measure of central tendency, and we indicate some measure of dispersion. So here we're talking about having some variability around our guess of where the mean might be. And that experimental variability or experimental error can arise for different reasons. One example might be that we have instruments in any field of science that are not entirely reliable. That is, if we take the measurement 2 times in a row, we might get similar outcomes, but perhaps not identical outcomes. And that's reflecting maybe some lack of perfect reliability in one of our instruments. Our instrument might be something like a physiological measure. It might be something like a survey. There are no instruments, typically, that would have perfect reliability, so some of the variability we would expect coming from here is going to contribute to variability in our overall scores. Another idea that we have is that we get sampling variability. If you can imagine taking a sample of students from our campus, and we want to measure how tall these students are, one sample will have a slightly different mean than the next sample. These are just random variations. Even if we had a perfectly reliable instrument for measurement, the sampling is going to generate some error. So lots of different sources of error or variability, separate and apart from our treatment effects. What we try to do as researchers in psychological science is minimize those last two sources of error so that we can more appropriately identify and isolate the treatment effect that is of interest to us. That's our independent variable. And we can try to isolate or minimize these effects, the other sources of variability, by controlling or holding constant the factors that are not relevant, or balancing them out by using randomization. And we talked about that in a prior session, the importance of control and balance whenever we're conducting an experiment. Individual differences in experimental error cause variability in both the within subject and between subject portions of our ANOVA, and by contrast, the treatment effects only pertain to the numerator, the between group portion. So let's think about the total variability, and I'll ask you to think this through with me. Early in the semester, we learned about a very important indicator of variability, and that was the sums of squares. We can take a list of scores, we can compute their mean, and ask to what extent does each score differ from its mean? And we get that deviate. And we do that for the next score, the next score, the next score. We get a list now of deviates right next to our list of raw scores. Once we have the deviates, we can square the deviates, and then we can sum the squared deviates, and that would give us our sums of squares. If we do this in any study, we get the total variability for the scores in that study, and that's going to be shown up here. What we're now going to learn how to do is how do we partition that variability so we can understand what's going to wind up in the numerator of our F ratio and what's going to wind up in the denominator of our F ratio. Conceptually, this is what goes on. The numerator will reflect the between group variability, and it will have 3 sources of variation. The treatment effect, which is really of interest, and as we said a moment ago, individual differences and experimental error, or experimental variability. By contrast, in the other section of our ANOVA computation, this would be the denominator, we have the within treatments variability, and that's going to be individual differences and experimental error. Note that what's missing here is the treatment effect. And the treatment effect is only influencing how the groups are differing from each other. It's not affecting the within treatment variability. Within a particular treatment, all the persons are receiving the same level of our independent variable. Okay, so here's the ANOVA, also called the F statistic for Fisher. So F is equal to the variability between groups versus the variability within groups. I'll try to do this by gesticulation one more time. Let's just say that we are going to run an ANOVA on two different groups. We could use the t-test for that, but we could also use an ANOVA. I'm going to draw my graph. Here's 0 on my graph. Here's the height of the first group on average. Here's the height of the second group on average. What we want to know is, how do these means differ? Is one group higher or lower than the next? And we can call that difference between the means a source of variability. Right? There's going to be variability between the groups. We also learned in our descriptive statistics that we not only report the means, but also some measure of dispersion. And now, instead of just plotting the means, I put on some error bars, shown like this. And the error bars can be small, the error bars can be wider, but whatever they might be, we can ask about the difference in mean relative to how much error we have. And that ratio, the variability between, that's the difference in means, versus how fat the error bars are, that's the variability within, will give us some indication of the F ratio. Remember, it's just a ratio, no big whoop. We can unpack this one more time and harken back to the slide that we had a moment ago. The F ratio is equal to this numerator, the treatment effects, plus these uncontrollable sources of error, or at least less controllable sources of error, the individual differences in the experimental variability, or the experimental error, over the individual differences and the experimental error. Okay, so that's the difference between the between and within subject if we unpack the F this way. Here's another way of saying the same thing. Sometimes it can be helpful to say the same idea a couple of different ways so that we can develop some really good intuitions about this, and we're not just mindlessly plugging through the numbers. We really want to understand what's going on in the computations that we're running. So here's the F one more time, and we have some systematic variation added to the error variation, and all of that gets normalized by the error variation. Not too different from the way that we thought about our chi-squares, where we normalized everything by the expected values. Here we're normalizing by the error variation, the kind of variability we might expect just by chance, even if our independent variable had no particular effect. Okay? So here the error variation includes both individual differences and experimental error from the earlier slide. I'll now just flip these two around, and here we go. Now they're flipped. And what we can remind ourselves of is that the systematic variation includes the treatment effects and only the treatment effects. So that's going to be happening up here. And we might use this as an example. We might say that if we want to understand maybe a four-group study, we can think about the important issue of depression. And we can think about perhaps trying to remediate depression by using Prozac. And if we're trying out Prozac and we're investigating it, we might have one group of 5 people that would have 0 milligrams, another group that would receive 1 milligram, another group would receive 2, and our final group might receive 3 milligrams. Frequently, this course is taught in a room where we have 4 rows of 5 chairs. And what we can think about is each of those different rows is getting a different level of our treatment condition. That's the level of Prozac. 0, 1, 2, or 3 milligrams of Prozac. Okay? That systematic variation is what we're doing with our Prozac manipulation. Then there's other variability in the room as well. We might have a particular sample that is very representative or less representative. We have individual differences and so forth. These are sources of error variation. Okay? And what we're hoping to do is get an F value sufficiently large that we could reject our null hypothesis, as we always do whenever we're hypothesis testing. So if we do have a null hypothesis, it would predict that there's no effect of our manipulation. Okay? And we'll see in just a moment that the null hypothesis, when we're talking about the comparison of means, is that all the means are equal, just as was true for the null hypothesis in the t statistic. So here, when we're thinking about the treatment effect, it is possible that the treatment effect is essentially 0. And if that's the case, then we have individual differences plus experimental error over that same quantity. Individual differences plus experimental error. In other words, we have some number over that same number. The F statistic would wind up in that case equaling 1, and we would wind up retaining the null hypothesis. Okay? So here again is the null hypothesis for any kind of ANOVA. We would say that the HO, or the null hypothesis, which says that there's a null effect of our manipulation, would have us come to the conclusion that mu1 is equal to mu2 is equal to mu3, mu4, and so on down the line. You would have a different mean, population mean, that is to say, for each of the different groups that you might be comparing. So the null hypothesis for the ANOVA, in the population, all means are equal. Just as a reminder, we're using mu's here because we are actually drawing an inference about the population, and population parameters are specified by these Greek letters, mu and sigma, mu for the mean, sigma for the standard deviation, an indication, again, of central tendency and dispersion. Here, very simply stated, is H1, or the alternate hypothesis, and that's simply not HO. That might be that at least one of these means is not different, at least one of these means is different from another. There's some inequality there somewhere. We haven't said where it is, we haven't specified the direction of that inequality. All we're saying is that this statement is not true in the alternate hypothesis. And using modus tollens, we in fact evaluate the null hypothesis. Remember that modus tollens was if P, then Q, not Q, therefore not P. Okay, so let's move on, and we'll consider a set of pictures to further explore some intuitions about the F statistic. That's Fisher's statistic. And we'll remember that the F statistic is this ratio, the between group variance over the within group variance. And our little mnemonic from a moment ago was that B comes before W in the alphabet, so that's how we can think about which one goes where when we are constructing our numerator and our denominator. Numerator first, that's the B. Denominator second, that's the W in within. Okay, here I'm going to take a moment and explain some color coding that's going to be relevant for this slide and the next two slides. It will also be relevant for future conversations that you'll be having in this course with regard to other variations on ANOVA. For today's session, we're actually dealing with something called a one-way ANOVA. And in a one-way ANOVA, we have only one independent variable. But you can have more complex ANOVAs that deal with two or more independent variables. So here we have only one independent variable. It might have 2 levels, it might have 3 levels, it might have 328 levels. But we have only one independent variable. So we'll be doing the one-way ANOVA here, and we're trying to capture what that's like conceptually by using different color coding. Here we have the variance between groups shown in green. We have the variance within groups shown in red. The total variability, shown in this pie, corresponds to, if you'd like to think of it this way, the total sums of squares. Remember, one more time, we have a list of scores, all of them, and then we can find their grand mean, and we can find the extent to which any given individual differs from the grand mean. That would be a deviate. We can square those deviates, we can sum those squared deviates, we get the sums of squares, and we can put that into a big pie. We're now going to partition that variability, as indexed by the sums of squares, into 2 halves just for the moment. We'll call that the red half within, the green half will be between. So the F ratio here will be equal to 1. Hopefully that's intuitive for you because the area represented by the green is equal to the area represented by the red. We have some area over that same area, that ratio equals 1, and we would need to have more of an effect size in order, or a larger treatment effect in order to reject the null hypothesis. So this would be very consistent with the null hypothesis. The F ratio would equal 1, and we would retain HO. Let's now keep all this the same and try a couple of variations on this. Let's see if we can do it this way. We would have, in this particular case, a smallish green area, so the variance between groups is really quite small, and the variance within groups has grown quite a bit in this case, so we have more variability within groups than we do between groups. I'll make a gesticulation that I hope will help us. So here are the two groups that we're comparing, and let's say that the first group gets a mean up that high, the second group gets up a mean that's almost as high but not quite as high. There's a little bit of a difference there, captured over here by a small between group difference, small between group variability shown in a small region of green. If we now put on relatively large error bars though, we have a lot of variability within this group, a lot of variability within that group. There's more variability within each of these groups than there was between their means. So now we have a large red area, that's going to be our denominator. We have a smaller green area, that's going to be our numerator. We have a small number over a large number, that's going to give us an F ratio less than 1, and that again will have us retaining our null hypothesis. Then finally, let's do this one more time. We'll take the last possible case, and here we have a relatively large green area, that's our between group differences. Now our two means are not that similar to each other, they're very different from each other, and we might have small within group variability. A small error bar here, a small error bar here, and a huge between group variability. Within is quite small, shown in red, that's going to be our denominator. Between is quite large, shown in green, that's going to be our numerator. A big numerator over a small denominator is going to give us a relatively large F ratio. We'll call it greater than 1 for the moment, and this now raises the possibility that we can reject HO. Whether we actually reject HO will depend on the critical value of F, just like it would on the critical value of chi-square, for which we use the chi-in function, or the critical value of t, for which we use the t-in function. We'll now be using the f-in function to find a critical value of F, and if our observed value of F is greater than that, it would also have to be greater than 1. We could reject the null hypothesis. Okay, so you might remember our old friend the variance. We've computed the variance a few different times. Even from the second week of class, we've been computing the variance. We need to determine the sums of squares if we're going to get the variance, and divide that by the degrees of freedom. And so let's see how we might engage in this partitioning. Here's the total variability as indexed by the SS. You will not have to memorize this computation, but that would be one of the ways that you could compute the total SS. We're going to partition this into a between subjects component that was shown in green a few slides ago, and a within subject component that was shown in red a few slides ago. And we have that ratio that we're going to be working with. The total sums of squares gets partitioned into a between subject component and a within subject component, respectively, in the numerator and in the denominator. Okay? We also have to be mindful of the degrees of freedom, because if we're going to be working with variances, you'll recall that the variance is equal to the sums of squares divided by the degrees of freedom. So our degrees of freedom will now be partitioned into a between subjects component and a within subjects component. Let's harken back for a moment to the study that we were looking at earlier. We were interested in Prozac. We had the 4 rows in our classroom, 4 rows of students, and we had 5 persons per row. So we had a total of 20 people in this hypothetical study on Prozac. They were receiving respectively 0, 1, 2, or 3 milligrams of Prozac. Okay? So we can think of n as being the total number of people that we had, and that would be something like, let's see, we had 4 rows and we had 5 persons per row, so that would be 20 people. So we'd have 20 minus 1, we'd have a total of 19 degrees of freedom. We can even partition the degrees of freedom by asking, well, how many treatment conditions did we have? And let's see, we had 0, 1, 2, and 3 milligrams of Prozac. Those are 4 different conditions. We'll call the number of conditions k. We'll subtract from that 1. So we have 3 degrees of freedom over here. And then n minus our 4 conditions will give us 20 minus 4 conditions, 16. So we have 3 and 16 degrees of freedom. And that number adds up to our total of 19, as we mentioned a moment ago. So we can even partition the degrees of freedom. Okay, so now what we'll do is try to put all that together and come to our first F computation. And as we said several times now, we have some between group variability that's shown in this row over some within group variability that's shown as the error term, as it's sometimes called. You can call this within group. This is between group if you like. And reminding us now here is that we have the sums of squares as an index of variability. We have the degrees of freedom. And when we divide the sums of squares by the degrees of freedom, we get the variance. We did that even during the first week of class. Here's something I'd like you to jot down. We have a new phrase to refer to the variance, and that's called the mean square. In other words, these were the squares, and now we've divided them by the degrees of freedom, and that gives us some kind of a mean squared value. That's abbreviated by an ms. So we have an ms for the between group component. We have an ms for our error term, which reflects the size of our error bars. And the F ratio is simply that number over that number. Okay? So from the top, we have the sums of squares here, divided by the degrees of freedom, gives us our mean square, which is our variance for the between subject component of the F statistic. And we have 37.2 divided by 16, giving us the variance, or the mean square, for our denominator, our within subject component, shown in red in the earlier pie chart. Then over here, we can take the ratio of those 2 numbers and we get 7.82, and it turns out that the sig value that we would see in SPSS, the probability of getting that just by chance, is really quite small. It's quite a bit less than our standard 0.05 alpha level, our criterion alpha level, and because it's less, we can reject HO. Just a heads up, I've put reject HO here to help us understand how we would think about this in the context of hypothesis testing. One does not normally put the reject HO designation inside of the F table, this ANOVA table, but I've done it here just for clarity and to harken back to some other hypothesis testing that we've done before. So here's the summary table for the ANOVA, which is also called the F statistic. And during the next several classes, we're going to be spending a lot of time filling out these kinds of tables. What I'd like to do is just ask you to think about a few of these numbers for right now. The degrees of freedom being 3 and 16. We talked about where those numbers came from. The observed value of f was 7.82. We're winding up rejecting HO. I'm going to break out of this just for a moment and show us a picture that I hope will say 1,000 words. Okay, so we've seen these distributions before. Here what I've drawn is the f distribution. At first glance, it might look very similar to the chi-square distribution. And the reason for that is both the f distribution shown here and the chi-square distribution shown previously are positively skewed. They are unlike the t distribution, which is symmetric and somewhat bell-shaped. They're very unlike the Gaussian or normal curve. When we were using the z-scores, those are perfectly symmetric. Here, the f statistic ranges from 0 to positive infinity, and it has this positive skew, this long tail off to the right-hand side. We might ask ourselves just to think a little bit intuitively about why the range of the f statistic would be like that of the chi-square statistic, from 0 to positive infinity. And the answer is that we saw just a moment ago, we're really comparing or analyzing a ratio of two variances. There's the variance between over the variance within. Variances are based on sums of squares, and sums of squares cannot be negative, at least not in the real number system. So we really couldn't have a negative f value. In principle, you could have a 0, but you couldn't have a negative. And then to the extent that our treatment effect is very, very large, we would expect larger and larger values of our f statistic. So as always, we have the statistic on the x-axis, and we have probability on our y-axis. So some scores are really quite probable just by chance, and it turns out that if we have essentially no effect of our independent variable, and that's what we would expect if our null hypothesis were true, we would wind up with f values that are approximately 1. To the extent that we're getting values more out this way, then we have the probability, or at least the possibility, of landing in the rejection region. Remember that there's a critical value right over here that separates the extrememost 5% from the more typically occurring 95%. And we're interested to contextualize our observed value of f, which in this case was 7.82 from the chart that we had just a moment ago. And that exceeds our critical value of 3.24. One of the other ways of thinking about this is the ratio of the differences between the means, that's going to be in our numerator, versus how variable the scores are even within a group. And as these numbers come down, our numerator is getting, our denominator is getting smaller, our variability is getting less within each group, and as the group means are getting wider, further and further apart, our numerator is getting larger, and that's going to push us out in this general direction. So a couple of numbers here. 3.24 was the number that we had to beat. That was the f value that we had to exceed to wind up in our critical region. Let's just remind ourselves where that comes from. The 3.24 is the critical value that, like all critical values, will come from a inv function. That's inv. We did chi-inv, we've done t-inv. Now we'll take a moment to do the f-inv. So let me break out of this and open Excel. And let's just remind ourselves of some of the values that we would need to create any kind of critical value. So we always have to remind ourselves of what the criterion alpha level is, and in this class it's always going to be 0.05. It's a standard used in many of the sciences, not just in the science of psychology. So we're willing to run a 5% risk of having a type 1 error, that is falsely rejecting the null hypothesis. Here we had different degrees of freedom, and this is something that's new for the ANOVA. We don't typically have more than one degree of freedom indicator, but here we have one for the numerator, and here we have one for the denominator. That was between subjects, was 3, within subjects was a total of 16, and that added up to 19 degrees of freedom. Then what we need is the observed alpha level. We're hoping that this might be below 0.05 so that we can reject the null hypothesis, which of course is that all mu's are equal. Here, instead of using the t-inv, or the chi-inv, or the norms inv, we're going to be using the f-inv because we're doing an f statistic. So let's come on over to here, and we'll put in equals f-inv. We'll open a left paren, and we get prompted for the quantities that we have over here. As always, we want to know what probability we're interested in. That's our criterion alpha level, and that is 0.05, as always. And normally we get prompted for the degrees of freedom. Same thing is true here. The only new wrinkle in today's conversation is that we now have two different degrees of freedom. We have one for the numerator and one for the denominator, And the convention is that we always put them in that sequence. So we'll put in 3 as the degrees of freedom for our numerator, shown here as degrees of freedom 1. And then we'll put a comma to add our second degrees of freedom, which is the degrees of freedom for our denominator. And we can close that off. And we wind up with a 3.24. That's the critical value of f, the value we would have to exceed if we're going to reject the null hypothesis. So one other reminder about this. Here we're being prompted for 2 different degrees of freedom, one for the numerator, one for the denominator. It really does matter what sequence we use when we're inserting that information. Excel always assumes that we're putting in the numerator's degrees of freedom first and the denominator's degrees of freedom second. Just to show you, we'll come up with a very different number if we put in these in the incorrect and reversed order. So let's go ahead and do that. I'll now say equals finv. And instead of putting in this one first, I'll put in that one first. There's my 16. I'll put in a comma. And now here's my 3. What you'll see is that I get a number that looks innocent enough, but it's actually not the same number. It was 3.24 a moment ago, and now it's 8.69. So those would be very different values to beat. And if we had used an 8.69, then you can see that we would have had to get a much larger value. Let me put this up. We would have had a critical value over here at the 8 and something level, and we would have been at 7.82, we would have retained. So it's critical that we actually insert the degrees of freedom in the appropriate sequence. Numerator first, denominator second. Okay, let's now bring back this information from our PowerPoint. Okay, there's where we were, and we saw now pictorially how that 7.82 was contextualized in an entire family of possible f values on the distribution that corresponded to 3 and 16 degrees of freedom. Here's another way of saying the same thing. We can take a look at some of the scores that we might get for any 4-group study. Let's take another example. We've been using the Prozac example for a little while now, just to get a little bit of conceptual variability. Why don't we see if we can change to a new topic where we might be interested in cognitive performance. And we might try to enhance cognitive performance by using different kinds of treatments. In this case, we'll again go with 4 groups. We'll again go with a total of 20 students, 5 in each of the 4 groups. But some of them will be receiving absolutely no cognitive training whatsoever. That'll be our control group. Others will be receiving a kind of cognitive training called the lumosity treatment. And this is something that you might find online. You don't have to look it up online, but you can learn about lumosity online. Another interesting possibility is that we can actually get better in our cognition by playing video games. And we've had colloquia in our own department that have shown evidence for that claim. And then also we can talk about the possibility of improving cognitive performance just by getting aerobic exercise. There are some researchers in psychology who are financed by the National Institutes of Health and are very interested in determining to what extent aerobic exercise improves cognitive performance. So we have these 4 different groups, each with 5 persons in it: aerobic exercise, video game, lumosity, and a control group. And we can ask, are these means different from each other in any way? The null hypothesis being that in the population, all of these means are going to be equal. Okay? So what we might see just by quick inspection is that we have a low performance level here. We're assuming that lower numbers correspond to worse performance, higher numbers to better performance. It looks like the aerobic exercise group is scoring best on this, and it looks like if we compare the differences in means in the context of relatively small margins of error, as indicated by our standard deviation, there's a good chance we would have a significant ANOVA here for this particular study. So now you get the opportunity to see what this might look like in Excel, and in the not too distant future we'll be putting this into SPSS as well. Okay, so why don't we pause for a moment, have you stop the video, and make a note to yourself of what is clear and what is not clear. Okay, welcome back. And now we'll be talking about the equal variance assumption. This is something that we've seen before. We've used the equal variance assumption when we were talking about t-tests not too long ago. The ANOVA is based on a few assumptions, and the equal variance assumption is one of the 3. The other 2 would be that we have normally distributed data and that we have independence between the scores in our data set. The most important of those 3 would be the equal variance assumption, sometimes called the homogeneity of variance assumption. And for the ANOVA to be appropriate, the variance or the dispersion how fat those error bars are, must be comparable across the groups or conditions that we might have. SPSS can help us to understand whether to retain that assumption or reject that assumption. So we're starting out with an assumption of equal variances. As we've said before, we have a null hypothesis that is really a prediction about central tendency. Are the means the same? This assumption is really a prediction about whether the variances are the same. And that might be a safe assumption, that might not be. SPSS can help us by putting out, as you might remember, the Levine statistic. We've seen this once before. It becomes a particularly salient problem when we're dealing with ANOVAs, because when we have ANOVAs, we might be analyzing the variance on many different groups, not just two groups. And the more groups we have, the more likely it is that just by chance we'll get very different variabilities across a particular pair of groups. So Levine will help us with that, this test of equal variance or the test of homogeneity of variance. As we've seen before, the critical piece of information that we have to pull off of the Levine statistic is its sig value. And remember that our rule is that whenever we're looking at sig values, when the sig value is less than 0.05, we reject something. In this case, the Levine statistic is asking us to think about an equality of variance, and we can either retain that assumption of equal variance or we'd have to reject it. In this particular case, we're going to wind up retaining the equal variance assumption because we have a sig value that's greater than 0.05. Had it been the case that this value was less than 0.05, that would suggest that we might have one set of error bars that's really quite big like that, and another set that's really quite small. And those variances might be so different from each other that Levine would say that it's really not fair to call them equal or even comparable, and we probably shouldn't engage in this kind of ANOVA, or we'd have to make some kind of a correction to deal with this. In this case, we're going to retain the equal variance assumption. So let's see if we can summarize that. As we've said before, there are these two-step processes. Step one is to decide whether we retain or reject the equal variance assumption, and the Levine statistic can help us with that. And we'd always use the same rule, that is, the 0.05 sig level will be our arbiter. If that sig value is less than 0.05, we reject something. If the sig value is greater than 0.05, we retain something. In this case, we're either rejecting or retaining the equal variance assumption. After having looked at the dispersion and set the stage for asking the question about whether it's even fair to compare the means to each other, we then go on to a comparison of means, evaluating the null hypothesis using modus tollens, and we can say that, as we always do, if the sig value associated with our between groups analysis is less than 0.05, we would reject the null hypothesis in that case. Okay, so those are the two steps, and here we're looking at a comparison between groups. In this particular case, we're looking at cholesterol counts. It's an interesting measure. Some psychologists are interested in cholesterol counts. It might be the case that a health psychologist who also has a developmental bent is interested in understanding how cholesterol varies across the lifespan. And we might compare, for example, three groups of participants: younger adults like you, middle-aged adults, and older adults. And we might ask, are those three different from each other in their cholesterol counts? And so we'd have a between groups analysis, a within groups analysis. We can fill out our F table, and we might come to the conclusion that in fact we have a statistically significant difference as indicated by this sig value. The sig value is less than 0.05. Our rule is that we reject. Okay. All right, why don't we pause the video camera just for a moment, have you stop the video, and make a note of how much of that was clear or what remains unclear about the issue of equal variance. Okay, welcome back. We'll move on to our third and final component of today's session, and this is on cumulative type 1 error, a new kind of error that arises just for the first time when we start looking at ANOVAs, when we have more than two means to compare. And a solution to that problem of cumulative type 1 error is going to be something called post hoc tests, again brand new to us today. So let's jump right in, and let's remind ourselves about one of the benefits of the ANOVA. It's very flexible. We can use the ANOVA to compare at one time a whole bunch of means. It can be hundreds of means, it can be thousands of means. If we do in fact get a significant F value, what that tells us is at least one of the means is different from another one of the means. In fact, I often jokingly say that if the ANOVA had a theme song from Sesame Street, it would be one of these things is not like the others. And this omnibus ANOVA, as we sometimes call it, tells us whether there's a difference anywhere in our data set. Any one of the means is different from any one of the other means, and that can be helpful to know. It's a very efficient way, a very flexible way of finding out that we do have a difference or that we don't have a difference. The problem, though, is that the omnibus f, this overall f value that we've just been computing, doesn't tell us where that difference might be. It doesn't pinpoint the difference. We'd actually need to do that by looking at a series of t-tests and making pairwise comparisons. So that's one of the limitations of the f statistic. It does not indicate which one is different from which. It only tells us that somewhere we have at least one mean that's different from at least one other mean. So that's one of the limitations that we have, and we'll try to correct that too with the post hoc test. Here's the second issue that comes up. If we conduct an experiment a sufficiently large number of times, we are bound to find a significant f value just by chance. Notice, please, that I put significant here in quotes, and I'm also using air quotes. And what we mean here by saying significant f value is that, yes, just by chance, we're likely to find that one mean is different from another if we compare enough means. This should be fairly obvious to you. If you imagine a perfect Gaussian distribution, and it has some mean in the center of its distribution, if we generate random numbers with that mean and with that standard deviation, some of the numbers are going to be right at the mean, some will be a little bit lower, some will be a little bit higher. Every once in a long, long while, we'll get an extreme score down on this side, we'll get an extreme score up on this side. And those will happen with known probabilities because we know something statistically about the likelihoods associated with the Gaussian distribution. So over here what we're saying is that because we now have many, many chances to get an extreme score, we're likely to get one just by chance, and the more comparisons that we make as our ANOVA's experiment gets bigger and bigger and bigger, then we can say that we have a greater chance of getting an extreme score just by chance, even if our null hypothesis really is true and our treatment is doing absolutely nothing. We will occasionally get an extreme score just by chance. Okay? So in other words, as we run more statistical comparisons, the probability of finding a significant result accumulates, and that's an important word. So we have this problem of cumulative type 1 error. That is, getting an incorrect outcome, rejecting the null hypothesis just by chance. That's more and more likely as we run more tests. We sometimes call this family-wise type 1 error. We sometimes call it family-wide type 1 error. I've seen it stated many different ways. So this is the increase in the likelihood of erroneously rejecting the null hypothesis when multiple statistical comparisons are made. One more example might really make this clear. Imagine that we have a lottery in which there is a container that has 100 ping pong balls. Every ping pong ball has one number on it. The number is between 1 and 100. So there are 100 ping pong balls, and you're playing this lottery, you're hoping that your number might be drawn. If we give you one lottery ticket with one number on it, your chance of winning that lottery is 1 in 100, very obviously. But if we let you play it a second time, and we give you an additional lottery ticket, now you have 2 unique lottery tickets, now you have a 2 in 100 chance. If you play it 3 times, you have a 3 in 100 chance. Notice that your probabilities are accumulating. This is very much analogous to what happens when we're comparing many, many means. We have an accumulation in the probability of finding an effect just by chance, and we need to control for that somehow. So one way that we do that is by introducing post hoc tests. These will control for this unwanted accumulation of type 1 errors. Each procedure for correcting the cumulative type 1 error involves a slight modification to the critical value. A little while ago we saw this distribution, that was the F distribution, and we had a critical value over here on your right-hand side. And we had to find an F value that exceeded that critical value in order to reject the null hypothesis. What the post hoc tests do is they basically move that value back a little bit further to make it a little bit harder to beat the number to beat. That is, a little bit harder to reject the null hypothesis. And there are different computations here. There's one called the Chaffee, there's one called the Tukey, there's one called the Dunnett. These are the names of different statisticians that have made different kinds of adjustments to our critical value so that we can somehow compensate for the accumulation of type 1 error that occurs whenever we have many, many comparisons being made. And this is often the case when we're running an ANOVA. Okay, so that's a lot of different ideas. I wonder if we can begin to summarize it this way. We won't go into how these different post hoc corrections, the Dunnett, the Chaffee, and the Tukey, differ from each other. Most people agree that the Chaffee is the most conservative of these corrections. That would move the critical value furthest out to the right in that distribution, giving you the largest critical value, the most conservative correction that we might have. Okay? So what we can say is that these post hoc tests are important for 2 reasons. First, the post hoc tests allow us to see exactly which pairs of means differ from each other. Remember that the ANOVA only tells us that one of these means is different from the next. We'd actually have to run a bunch of t-tests, all of which would be corrected by some kind of post hoc adjustment, maybe a Chaffee adjustment, and we could see exactly where the difference is. Maybe it's between the, for example, 7th mean and the 38th mean. That might be the only pair of differences that we find. They help us pinpoint where that difference is. Secondarily, they control for this accumulation of type 1 error by moving the critical value further off to the right, making it harder to beat the number to beat. Here's an example, getting back to our cholesterol count, and we'll close with this example. Earlier we mentioned that a health psychologist with a developmental psychology bent would be interested in tracking cholesterol across the lifespan. How is it that this cholesterol level maybe accumulates across the lifespan? And we can look at young adults like you, we can look at middle-aged adults, and we can look at older adults. We have those three groups. We can take cholesterol measurements on each of them, and we can make a whole bunch of pairwise comparisons. We can compare young people to middle-aged folks, young people to older folks. We can pull the middle-aged folks out here, compare middle-aged to young, middle-aged to older. There's some redundancy there. All of these now can be differenced, and we get a difference score here. And then we can ask whether those differences are significant. As you might see here, the young folks are significantly different from the middle-aged folks, and the young folks are significantly different from the older folks because these sig values are less than 0.05. By contrast, if we compare, for example, the middle-aged group to the older group on their cholesterol count, we come up with a sig value that is not significant, a observed alpha level that is greater than 0.05. So we would retain the null hypothesis in that case. We can, in fact, run a different kind of post hoc test using the same structure, but now we make a Chaffee adjustment. It's a little bit more conservative. It moves the critical value a little further out in our distribution, and you can see that we're now getting these sig values that are even further away from 0.05 than had been the case over here with the Tukey adjustment. So the Chaffee is, in fact, a relatively conservative correction. Okay. So that was a lot of information. To begin to summarize, we talked about a conceptual introduction to ANOVA. This idea that we want to compare means, we want to run an inferential statistic across potentially many, many groups. Some of the complications that arise would be the equal variance assumption. As you have many, many groups, it might be the case that we have unequal variances, and the Levene test will help us with that. If we do have equal variances and we make our comparisons, we need to figure out where the particular differences might be if in fact our omnibus test tells us that there's a difference somewhere. And we can use post hoc tests to pinpoint where those differences are and to also correct for cumulative type 1 error. So I hope you'll now take note of what has been very clear to you and what has been less clear. And that's an important point. Your metacognition is just as important as your cognition is. That is to say, your ability to think about your thinking is just as important as the thinking is itself. I hope you'll make your notes, and I look forward to seeing you in class.